Welcome. In this lecture, we are going to talk about digital voltage mode control design for shaping output impedance in a buck converter. So, in this lecture, we are going to talk about loop shaping objective in digital voltage mode control. These things we have already discussed. We want to show the design of digital voltage mode control using for shaping the output impedance and the frequency response case study for closed loop output impedance. So, here the digital voltage mode control, we are taking the same practical case study power stage, which will be used for experimental case study. Okay. And here we will take both 3.3 volt input as well as 5 volt input and 1 volt output as well as 1.8 volt output. And this we have discussed earlier, that this we have to implement using FPGA when you go for digital control voltage mode control implementation. This thing also we have discussed, and there is also a feedback gain in a practical converter, and which is because of this resistive divider, and this is also here that we have discussed. Now, we have also discussed in the previous lecture the design aspect. So, we are not going to repeat the design aspect, but here what we are going to do, this is our open loop output impedance, this is our open loop output impedance, which we call Z0, and we want to get closed loop output impedance. That means, and what is this for open loop output impedance? It is minus V0 tilde by the external load tilde when we are considering duty ratio to be 0, input voltage perturbation to be 0. But when you are talking about closed loop, then the loop is closed. So, it will be again minus V0 to I0, but in this case we are only talking about input voltage 0, and it can be shown that this is 0 output divided by 1 plus loop transfer function, that is this k dash loop. So, this is the loop transfer function here. Okay. So, how can we get the closed loop output impedance, which is the critical part for getting the load transient performance? So, now we have discussed in our lecture number 30 in our earlier NPTEL course that exact pole 0 stable pole 0 cancellation, which is very sensitive to system parameter. But when you talk about the closed loop output impedance, that means here we are shaping the loop transfer function to get what was our objective, to get our objective was we wanted to get this thing to be some gain, maybe some effective gain divided by S. That means, we want to get a first order loop transfer function, but that is we are shaping the loop. But when you talk about the closed loop output impedance, then we still have this open loop plus 1 plus this loop dash, which is here. So, that means, even though you shape the loop transfer function, you may not have direct control over the open loop output impedance. As a result, there is we saw there is a difficulty in the shaping output impedance, closed loop output impedance purely based. So, that means design based on pure loop shaping is not effective for shaping the output impedance. And again we are considering the loop shaping approach, and we are getting the PID controller design, which we have discussed in our lecture number 43. So, this is the open loop output impedance, the closed loop. So, the pure loop shaping objective is not perfect for closed loop output impedance shaping, because we have no control over the open loop output impedance, and which is highly sensitive to load resistance, because when the load resistance varies, so it is highly sensitive. But suppose if the converter is purely driven by the output current load, there is no resistive load, then the output impedance will be purely the parasitic of the inductor and capacitor. In that case, it will be more or less known, but still the output impedance by pure loop shaping objective is not the right approach. Then what to do? So, we are showing a case study. If we go for pole 0 cancellation and the simulation parameter, we are talking about 3.3 volt input and 1 volt output, and our desired bandwidth is FSW by 10, then this is the pole 0 cancellation. So, you can see there is sort of this particular part is sensitive to load transient overshoot undershoot. Okay. And if you vary the load resistance, there will be kind of variation, slight variation, because it depends on the input voltage and other factor. So, this is the output impedance by taking 1/10 of the switching frequency by stable pole 0 cancellation. But if we go by, this is the case where we are talking about the alternative approach. So, this is the alternative approach we are talking about, where we are not cancelling the stable pole 0 case. So, that means this is more robust approach, and we want to show that output impedance is sort of well damped. Not only that, because if you go back to this slide, so this particular thing, that there is a phase roll up from 90 degree to almost close to less than minus 40 degree, 45 degree. But here if you take, actually the roll up is not so sharp, and secondly the output impedance now become insensitive to load resistance. That means you can design this method for various load resistance, but the output impedance will be more or less same. So, that will also, that can achieve very nice load transient performance using this alternative approach. So, if we consider this pole 0 cancellation, that output impedance shaping, now for 5 volt input and 1.8 volt output, we are making a load transient. That means we want to see the output impedance for both 13.5 and 0.32. So, you can see that there is a this particular output impedance, particular this region if you consider, and if you go back to our alternative approach design, which results into this Kp, Ki, Kd, if you go by the method that we have discussed, and these are the particular case study 5 volt input, 1.8 volt output, then you see again the load resistance for two different resistance, the output impedance, closed loop output impedance is more or less identical. So, it means this alternative approach can well damp the output impedance. We can further play with the shaping output impedance by suitably considering the derivative gain, which is nothing but a fraction. Here we took Kd in continuous time to be fraction of 2C. We can increase, we can take Kd to be maybe 0.5 C, we can play with this, you can get better output impedance. But only issue, if you increase too much in practical hardware, it may also try to inject the noise, and when you go to digital, where there is no pure derivative, it is basically a discrete function, because if you go to KDD, actual Kd into sort of dV0 dt, although there is a band limited derivative, but in discrete time it will be V error n minus V error n minus 1. So, since there is a one cycle, the voltage will be constant. So, this will not be exactly this unless the sampling frequency is very high. That is why we may not opt for a very large value of capacitor, which may create some kind of delayed effect, because if the actual voltage is out deviating, if you take the derivative, but if you take the sample here and here, you will not get the actual derivative action, okay, because you are losing the information in between. So, we are keeping a conservative choice of 0.2. So, in summary, we have discussed loop shaping objective in voltage mode control. We have considered design of digital voltage mode control for output impedance shaping, and we have considered few frequency response case study for closed loop output impedance. In a subsequent lecture, the next lecture, we are going to show hardware experimental result for loop shaping, that means the output impedance shaping result. How does it look like, the load transient performance, that we are going to consider in the next lecture. That is it for today. Thank you very much.